So in this lesson, we're going to look at atoms and how they actually don't stay as atoms a lot of the time. Instead, they become ions. And they become ions because they are more stable as ions than as atoms. So for example, sodium atom, which has an electron configuration of 1s2, 2s2, 2p6, 3s1, it is more stable if it has 8 valence electrons, because most atoms, their ideal state is when they have a full octet or 8 valence electrons. And so what sodium's going to do is it's going to lose that 1 valence electron, so that now when it becomes sodium with a +1 charge, it has 8 valence electrons, 2 in the 2s sublevel and 6 in the 2p sublevel. In contrast, chlorine has right now as an atom 7 valence electrons, and it actually wants 8. And so it's going to gain 1 valence electron, so it has 8. So let's see how we can actually use the periodic table in order to predict the charges of ions. So here's your periodic table, and if you notice for your alkali metals, that group 1 all the way to the left-hand side, for example, hydrogen would be 1s1, lithium would be 2s1, sodium would be 3s1, so they have 1 valence electron. Your alkaline earth metals, group 2, therefore have 2 valence electrons, because they'd be 1s2, 2s2, or 3s2, or 4s2. The group starting with boron, I'm going to skip over the transition metals. The group starting with boron has 3 valence electrons, and so I'm hoping that you're seeing a pattern now. Okay, they have 3 valence electrons because, for example, aluminum would be 3s2, 3p1, so the 2 plus the 1 gives you 3. Okay, now 4, 5, 6, 7, and then 8 for the noble gases, because 8 is great. You have a perfect octet. Now, transition metals. How many valence electrons do transition metals have? Well, transition metals, because the D sublevel starts 1 energy level lower, anyone in any element in the transition metals is going to have 2 valence electrons. However, I'm going to show you how to predict charge right now for all these other groups. We can't predict charge for your transition metals except for 2 exceptions, okay, which I'll have you write down in 1 second. All right, so if you look at lithium, lithium wants the electron configuration of a noble gas. So it can either lose 1 valence electron to get the electron configuration of helium, or it could gain 1, 2, 3, 4, 5, 6, 7 to get the electron configuration of neon. Well, it's easier to lose 1 than gain 7 valence electrons. So that entire group with 1 valence electron, its charge when it becomes ions is going to be +1. Okay. For magnesium, it can either lose 2 valence electrons to get the electron configuration of neon, or it could gain 1, 2, 3, 4, 5, 6. So it's going to lose 2, so it's going to have a +2 charge. Okay. The next group, as you can see, would be +3, because it's easier to lose 3 valence electrons than gain 5. I'm going to skip the group 4 for A, because it's equally easy to lose 4 or gain 4 valence electrons, so we're going to skip that. Now that I'm in group 5 with 5 valence electrons, is it easier to lose 5 valence electrons or gain 1, 2, 3? Well, in this case, now it's easier to gain 3, so the charge is going to be -3. So I'm hoping you're seeing a pattern. +1, +2, +3, skip group 4, -3, -2, -1. Now the charge of your noble gases, remember they have a full octet, and so they are going to have no charge.